Okay, it is my great pleasure to introduce Amir today. One of the real pleasures that we as academics have is seeing students come through the mill and do so with extremely good results like Amir has. Amir was a real find for us because he actually did his undergraduate degree in Isfahan, right? And then moved on to a Master of Science in Tehran University of Science and Technology. And then decided to go out and work in industry for, was it about 4 years or so?
Yes, 4 or 5 years, yeah.
But decided then to come to New Zealand. I think that was really neat for us, although it took almost a year, I think, to get through the whole visa issues.
Yeah, he has a nuclear bomb in his pocket.
He has a what?
A nuclear bomb in his pocket.
So when Amir arrived, he had actually started his PhD in the 6 months prior to that because he insisted on sending reports on various aspects of stuff that he was planning to do for the PhD. And that was a real indication of Amir's tenacity and dedication to the work. I need not say that he has achieved fantastic results because we all know that. He has been really involved in the lab culture, in producing papers and helping many people with a whole variety of projects. And I think Amir is a real role model of how the work within the ABI ought to flow. So, yep, I won't take up any more time because I know Amir has over 80 slides to get through. And,
over 100.
Over 100. Okay. So Amir is going to give an overview of his thesis work. That is why it has so many slides, because he did so much during that time. So it's over to you.
Thank you very much, Paul, for the nice introduction. This is a bit about my background. Paul mentioned that, and here is the time that I finished my Bachelor of Science. I started my Master of Science in Electronics. For my Bachelor, I did my project in speech processing. It was my first time encountering with signal processing, which later became my favorite topic in engineering. Then I started to work in the second year of my master, and I continued working until the time I came here to New Zealand to continue my PhD. For my work, I mainly was involved in hardware implementation of signal processing and image processing algorithms. For my master, I did signal processing, image processing for cardiac imaging and ECG signals. At the time, it was a method for understanding body surface potentials, relating that to electrocardiogram signals, and then understanding myocardium infarction. When I started to work, I mainly used a new technique or a new engineering concept for doing hardware implementation, which was an excitement for me and very interesting topic. When I found the PhD here, which was the combination of signal processing, image processing, and hardware implementation, I felt that this is what I'm supposed to do for my PhD. And this became my real motivation in the life to work harder, to do better, because it was something that at the time I felt, and I still believe, that it was made for me. The topic was very good. I really liked the type of work in the ABI, and I was very fortunate, lucky to find fantastic supervisors here. So it was where my journey started. Here on the left is my Master of Science thesis defense, and on the right is one of the outputs that we had in one of the companies I was working with for a signal processing device that we made there. My PhD is a combination of all those techniques to understand the behavior of tissues. As you know, at ABI, we have computational models. computational models need to have interaction with real tissues. And this comes through experiments. This is the basis of having a computational model. We need data to validate the models, to inform the models, and to improve the quality of the models. Models are only good enough if we can provide good data for them. And this was where my PhD started. This was understanding the biomechanical behavior of soft tissues. In our case, was skin and breast. Using camera systems, we can take images from the tissue. By analyzing the images, then we can understand properties such as stiffness or surface strain, which then helps us to understand the behavior to use that in computational models. The current methods weren't useful for this purpose. They are not either accurate enough or they cannot provide enough robustness that can be used in this application. That was the reason that we started to develop completely new methods that can address these limitations. Methods that can measure the tissue deformation under real condition in vivo, and then and under condition that we can get highly accurate results out of them. To address these limitations, we needed to tackle this problem from different aspects. This project contained image processing to understand and analyze the deformation in a single camera. Then we had instrumentation to build a device that can capture images from the tissues to be analyzed. By having cameras, we enter to the computer vision area, which is using cameras to understand the 3D behavior of an object, in our case tissue, and understand how it's behaving in a 3D environment. And then was hardware implementation, because when we have this setup and we want to analyze the output, because of the complexity of the outputs, we need to have higher computation power. And to reduce the time, parallel processing was an option that we could have used. These are 4 aspects of my PhD that we tackled during the 4 years of my PhD. For the image processing side of my project, one of the objectives was to address the limitations of 2D deformation measurement algorithms. In this case, we wanted to use the algorithm to find deformations in 2D, and the current algorithms were performed very poorly in skin tissue. That was the motivation for us to develop a new method for measuring this. We also needed to know the performance of algorithm in real working condition. That was other motivation to understand that how an algorithm can perform when we are using that in a real working condition. One of the other challenges and motivation for us was to develop a method that we don't need to prepare the skin for our measurements. It was the purpose that motivated us to develop a method that can use intrinsic features for tracking of the tissue. Performing motion correction was one of the other aspects and objectives of our project. In this case, because we have a camera that is taking images from the tissue, either the person might move or the camera might move. So we needed a method to remove this unwanted motion from the images. At the end was another aspect of measuring 3D deformations when we have a volume, such as, for example, in OCT or MRI. A new method was needed here to understand the behavior of tissue for volumetric deformation measurements. These are reflected in my thesis. One chapter was to develop a subpixel image registration algorithm for addressing 2D deformation measurements. The effect of camera setting was investigated on the accuracy of the measurements to give a practical view of an actual experiment. Subpixel measurements were performed using only intrinsic features for in vivo skin. This subpixel image registration algorithm was used to perform motion correction videos, and a new method was developed for accurate and fast volumetric deformation measurements. The other aspect of my PhD was to develop an instrument to measure tissue deformations in vivo, and the output was a device, a low-cost handheld stereoscopic device consisting of 4 cameras that can capture videos from the tissue to be used for the measurements. For the computer vision side of that, the motivation was to use this technique to measure 3D, the shape of the tissues, to understand 3D deformation in vivo. And in my thesis, we developed 2 camera calibration techniques to make it possible. One of them was addressing multiple camera calibration, and one of them was to use a model-based technique for improving the camera calibration. The final objective was to combine all together, use hardware implementation to make algorithms faster, and this was achieved by suggesting how hardware can be used for this application and how hardware can help to speed the computation time of our algorithm. So this was the outline of what I did in my thesis. In my presentation today, I'll only discuss the image processing side and computer vision side of my PhD. Because of the time limitation, I won't discuss anything about what we did for instrumentation and hardware implementation. However, I would be happy to discuss that later if you were interested to discuss about those. So the first section is image processing, and subpixel image registration was the first topic here. A bit of theory about what does it mean to do subpixel image registration. I try to make that simple. Here we have pixels of image. On the left is image 1, on the right is image 2. Image 2 is the shifted version of image 1 and is shifted by 2.7 pixel. For this we call it subpixel because 0.7 is not an integer value. Here we have 2 pixel shift, which is the integer part, and 7.7, which is the subpixel part of the deformation. The aim here is to find this deformation, this shift in the images. These are the usual methods that have been used in the literature for finding subpixel shifts. Some parts are for finding the integer shift, which was, in this example, was that 2 pixel shift between the 2 images. Cross correlation is the most common way of doing that. Normalized cross correlation has some advantages over the cross correlation, but it's computationally more demanding. Then phase correlation and gradient correlation are new methods proposed to address some of the limitations that we had in normalized cross correlation and cross correlation that was dealing with intensity values and in low textured images. Then normalized gradient correlation and orientation correlation are again new methods that are proposed to address again the limitations of these techniques in addressing poorly textured images. For finding the subpixel shifts, usual methods are either using interpolation in a spatial or frequency domain. Care fitting to the output of the cross correlation is one of the other methods used for finding the subpixel shift. Analytic solution and phase-based solutions are the other 2 methods of finding the subpixel shift between them. Our method was based on finding first integer shift using a new way of gradient correlation using Savitsky-Golay differentiators. And we suggested some improvements in the phase-based methods of finding subpixel image registration, subpixel shifts between the images. So in overall, our method was a 2-step method. In the integer part, we proposed a new method using Savitsky-Golay differentiators in the gradient correlation, and in the subpixel part, we proposed some methods to make that more robust to the noise. Using the integer part, in our method, when the integer shift has been found between the 2 images, in this example was 2 pixel, the image is shifted back to make the amount of shift between the 2 images less than a pixel. And then we can use phase-based information to find the subpixel shift between the images. In this case, it's done in this way to avoid doing phase unwrapping, because if it is larger than 1 pixel, phase wrapping will happen in the images. Then subpixel shift is found between the images, and the overall shift will be the addition of the integer part and the subpixel part. This is an overview of the method developed in this section. The method then was tested on some standard images. These are the example of images we use for our tests. There are 7 Landsat images. The quality has been increased for the visualization purposes, but the actual intensity range is not that good in the original images. In this method, the images are divided to some sub-images. Sub-images are a smaller version of the image, and the shifts are found for each of the sub-images over all the images. This is a comparison of our method compared with the other available methods in the literature. Most of them are the state-of-the-art methods for finding subpixel shift. In this table, the shifts, the errors are estimated for shifts smaller than 1 pixel. It was tested on 2,400 sub-images of the images that I've shown you as sample images. As you can see in the final column here, the performance of our method is at least 4 times better than the second available method, which was proposed by Stone et al. This method proposed by Stone et al. Is using a phase-based method for finding subpixel shifts between the images. And this is for shifts smaller than 1 pixel. This shows that how our method could improve the phase-based methods for finding subpixel shifts. When we apply larger shifts, in this table, the shifts were between 1 to 10 pixel. In this table, you can see that the method proposed by Stone et al. Fails in finding the shifts because basically this method cannot perform well in large shifts. Here we are showing that our method can perform both well for small shifts applied to the images and also large shifts here. In large shifts, which is more important and more common in measuring tissue deformations, our method could perform about 60 times better than the other, than the second available method in the literature proposed by Forosh et al. And this was a huge improvement over what else was available in the literature. This table was again generated using 2,500 sample images with different range of intensity values and different range of shifts in this application. The table was for noise-free images. To test that how our algorithm perform in the presence of noise, we added Gaussian noise, which is on the left side of this slide, and salt and pepper noise. The difference between them is that salt and pepper is more like on and off noise, and Gaussian has a Gaussian distribution density. Here you can see that for low levels of noise, our method is in pink here, can perform consistently better than the other available methods. And please note that this axis here is a logarithmic axis. So again, the changes, the difference between the performance of our algorithm is substantial when we are dealing with low level of noise, which is a typical type of noise that we get in the cameras that we are using. In the presence of high level of noise, again, our method can perform relatively well in both cases. In this, it was only in salt and pepper noise that one of the methods were performing better than our method in the presence of high level of noise. But it still shows that our algorithm can perform very well in the presence of noise. And you should notice that phase-based methods are usually very sensitive to the noise that are applied to the images. And to have an idea that what does it mean to have a high level of noise, here you can see an example of the original image on the left. And 2 images, which one of them is, in one of them a Gaussian noise is added to that, and in one of them salt and pepper noise has added. You can see that the output clearly shows that it was a high level of noise added to the images. We tested our algorithm by using that to measure rotation on the images. This is an example of how rotation has been measured. Rotation was applied to the images, and then the algorithms were used to measure that rotation. And we compare that with the other available methods and also the ideal rotation pattern that we had. In this slide, you can see on top left, it's the ideal rotation pattern that we expected to get, and the closer to that ideal pattern shows the better performance in finding the rotation here. These were also measured to find a quantitative way of measuring error, and you can see the rotation error on the top of the images here. Again, our method could perform very well in finding rotation here. And we should note that these methods are developed for finding translational shifts. And when they can perform good in finding rotations, it shows that they're robust in different aspects of finding shift in the images. This is the error measured for our method and other methods for finding the rotation. Again, you can see our method was at least 2 times better than the other, the second best method available in the literature. When this method was developed, the next step was to see how it will perform in real camera images. Up to now, we have tested that with synthetic shifts and images that were taken in an ideal condition. Here we tested that how this will perform in the presence of actual camera noise. Camera has some parameters that will affect the noise of the images. For example, gain, exposure time, and F number are the parameters that you can tune in the camera to change the image quality, and at the same time it will add noise to the camera images. So here the motivation was to understand how these parameters will change the level of noise and how this noise will affect the performance of algorithm in measuring deformations. This plot shows that by increasing the gain, we will increase the noise in the images. These are gains between 0 to 18 decibel applied to the images, and then the noise was measured for each of the images, and it shows that by increasing the gain, regardless of the exposure time, we will have increase in the level of noise added to the images. In these experiments, the lens cap was on, so the effect is mainly due to the change in the gain. Exposure doesn't change that too much because it doesn't have any lights. If we repeat the experiments with the lens cap off, we will see that increasing the exposure time will increase the noise. And you can see it's higher for higher level of noise here on the top. You can see, for example, in this case, the increase in exposure time has increased the value of noise. The estimation of noise has stopped here because the images started to saturate, and that's why I didn't continue measuring the noise in the images there. If you look closer at one of the plots here, for example, the plot that you can see on top here, if you have a closer look, you will see that you will have a slight increase in the noise level, and it's due to the saturation, the under-saturation, oversaturation, which is happening here. But overall, we can see that changing the exposure wouldn't change the image noise substantially. Another example that how this exposure time will change the noise in the images. Here, it was tested that when we have constant pixel intensity value, because pixel intensity value might change the level of noise that we are estimating in the images. Here we have kept that constant, and we've changed the exposure time to see that in the constant pixel intensity value, how changing the exposure time will increase the noise. And again, we can see a slight increase in the noise level, which means that when we have constant illumination, when we increase the exposure time, we are introducing a bit more error, more noise to the images that we have. But what does this noise mean for deformation measurements? We know that the noise will increase when we increase the exposure time. But when we analyze the deformation measurements, we found out that it's not very important or substantial for the deformation measurement algorithms to react to this noise. Which means that even though the noise is increasing when we increase the exposure time, the accuracy of deformation measurements doesn't change too much. And this shows that the algorithms are relatively insensitive to change in the exposure time. We tested again that how we can analyze the change in gain value to see that if it changed the accuracy of measurements or not. Here we kept the intensity value constant. We changed the gain value, and at the same time we reduced the exposure time and tried to have the constant intensity in the images to understand that how changing the gain will affect the output. We can see that by increasing the gain, our noise level will increase, and in this case it's more substantial than the exposure time that we had previously. And when we tested that on the algorithms, it showed that changing the gain will affect the accuracy of the measurements. Here we can see in images without noise, we have substantially smaller noise compared to when we add gain. And this is the effect of adding gain from 0 to 1 for different algorithms. In some of them, they are less sensitive to the noise, and this goes back to the nature of the algorithm that is dealing with the noise here. The outcome here was that when we want to increase the gain, we should be careful, because it will affect the deformation measurement output, especially for our algorithm, which was a more accurate algorithm compared to the other available methods. You can see the trend from gain 0 to gain 18 dB here, that's how it has affected 4 algorithms that we tested here. For our algorithm, the changes was more, even though it is increasing, it's still performing better than the other available methods in the literature. And this is again a log scale. Okay, so we have now a method that has been tested for real camera images. We know that how it's performing on the real camera images, and now that we have this, we can test this algorithm to see if it can be used for measuring living skin in vivo. The motivation here was that most of the methods available in the literature needs to have preparation for the skin, and this is an example showing that a speckle pattern were applied to the forearm to make that easier to measure the deformations. And we wanted to avoid this and wanted to test if our method can pick up deformations without adding any speckle on the surface of the image. This is the output of the measurements. You can see that the output has some problems, especially for the accuracy that was provided using this method. To test the algorithm, we designed an experimental setup here. A disk was placed here, and the rotational stage was used to move the disk, and then the algorithm was used to measure how much it has been moved. These images on the left show that, if the quality is good enough, shows that how deformation measurements was different from the average value. The reason that we compared that with the average value was that we have pixel shifts here, and we had applied micrometer shifts to the disk here. And because we have one camera, we can't measure the actual shifts applied. So we compared the average value to the value we had measured in the images to show that this method is performing well. And we noticed that the average error is more concentrated on the center of the images, and it was due to the lens distortion effects. We removed the lens distortion, and we saw that the error is uniformly distributed over the surface of the disk here, which resulted in a very linear behavior between the shifts applied and the shift measured in the pixel. In this case, it shows that even though we don't know how much we actually shifted the object, because we have a very linear relation between the shift applied and the shift measured, 1 in millimeter, 1 in pixel, it shows that the algorithm is performing well, that is able to detect this linear behavior between the two. In addition, the standard deviation of the measurements were very small, especially for values that are, the displacement are smaller than 100 micrometer, and shows that the algorithm is consistently have a good precision in measuring the deformation on the surface. Then the algorithm was used to successfully measure the deformations of the living skin without adding any speck to the surface. This is the direction of the change applied on the hand here, and the deformations were measured. And it shows that the algorithm could measure deformation using only intrinsic features. And this is the video showing that how this deformation has been measured for the surface of the skin. The values are ranging from large values here to small values on this side of the hand, and it shows that the algorithm was able to detect and measure deformations using only intrinsic features. The next step was to use this algorithm for correcting motion. And correcting motion is an important topic when you are dealing with live tissues. Either the instrument or the person might move, and we should be able to remove and correct for that motion. Again, we use an experimental setup to apply various range of shifts on the images. On the object here, we apply the rotations and translations to a flat object, and then use the algorithm to find the shifts. By finding the shifts on the top, then we define a transformation that maps the shifted image to the unshifted one to correct for the motion. In this method, after finding the transformation, we apply the inverse transformation to the image to bring it back and make it similar to what actually it was. This is an example showing that how this motion has been corrected. On the videos, on the video on the left are original images that have been translated. On the right, the area of the disk was motion corrected. And you can see that the area doesn't move. The background is moving, but the area that has been corrected for motion doesn't move. And it shows that how this algorithm was able to correct for translational motion here. Another example is that when we apply combination of translation and rotation, which is a more complicated movement of the object. On the left, you can see that the disk is moving, but on the right, the motion was corrected, and the object is still there. Another example is pure rotation. Again, you can see that how the algorithm was able to successfully find the deformation and correct for it on the video on the right. And it was also tested for real tissues. On top is a forearm moving, and on the bottom is it's a video, but you can't see any movement on that. If you closely look, you will see some changes close to the borders of the image. But it shows that the algorithm performs well even for live in vivo tissues. The next step was to extend this algorithm for higher dimensions. This was done by a very nice method proposed by Paul. At this one, we tackled many problems at the same time. It was both addressing that we want to develop a method which is fast, which is robust to noise. It can perform good in low texture images, and it can find large shifts. At the same time, we wanted to tackle all these problems, which all of them are difficult and challenging problems. This is basically the background, the theory of how this method is working. If you're familiar with image registration, you know that typically filters are applied in the spatial domain. Here we propose that instead of spatial domain, we can apply filters in the Fourier domain, which gives much more freedom to us. And we can design custom design filters and extract information that we want from the images. This was proposed for the integer part of the algorithm. We had some improvements for the subpixel part of that. Again, if you're familiar with the phase-based methods, we propose a way that can help removing outliers from the face to help better finding the subpixel shift between the images. We tested the algorithm with test volumes and images with different range of intensity values to show that how it performs in low intensity images to high range of intensity images and volumes. Before continuing to the plots, I need to define a failure rate to show you how the performance was. Failure rate was defined if we applied a shift and the algorithm wasn't able to find a shift within half a pixel from the actual value. So if it was larger than half a pixel, it was a failure. If it was less than that, it was a success. And the average value of the failures over all the tested volumes or images was defined as the failure rate of the algorithm. This is how the algorithm performed in the presence of Gaussian noise. This axis here is Gaussian noise increase from 0 to 50, and these are at different volume image sizes here from 60 to 64. And it shows that the method we proposed here, which are these two last colors here, could perform consistently better than the other method that we originally had and I explained previously. We are showing that by using this method, we can even achieve higher performance and accuracy in measurement of 2D shifts. But and if you take average from all the range of the Gaussian noise, you can see that again this proposed method could perform better than the other method that we had proposed previously. It wasn't the only thing that we could improve. By using this method, we were able to tackle the hard problem of 3D deformation measurements, and cross-correlation is the usual way of doing that, and you can see that cross-correlation almost failed at finding the shift between the two volumes, but our method is especially performing very well for larger sub-volume sizes here. The problem with cross-correlation is that it can't basically find shifts larger than a certain amount. You can see that how a cross-correlation is performing for low contrast, medium contrast, and high contrast images. In all of them, it fails after 2 or 3 pixel shifts between the volumes, which shows that the usual way that is very common in the literature is not good enough for these applications. We tested our algorithm to show that how the performance is in different range of Gaussian values, and again, we showed that our method is very robust in the presence of Gaussian noise, even up to high values of noise. Still, the error is less than a pixel in almost all the cases, which is a very substantial improvement. Now we come to the computer vision side of that. Now that we have an algorithm for measuring deformations, we need to do 3D measurements, which goes to the computer vision side of this. For computer vision, the main aspect is calibrating the cameras, understanding the intrinsic and identifying the intrinsic and extrinsic parameters of the cameras, which are relating to the parameters of the camera itself and the orientation and the position of the camera in 3D space, as well as lens distortion coefficients, which are related to the type of lens that we are using for 3D measurements. Camera calibration is mainly based on optimization process, which all these parameters goes inside an optimization. And then for each camera, we have 15 parameters that needs to be optimized during this process. The parameters need to be identified during an optimization process. And optimization is minimizing back projection error. This problem becomes very complicated when you have more than 2 cameras. That's why in the literature, you can usually see that they use only 2 cameras and are limited to maximum 3 cameras, because it will become 40 or 50 parameters that needs to be optimized, and the parameters have different nature and different units, which makes that very difficult to optimize. We proposed a method that could perform very well. This is how it performs, and this is the number of iterations in the optimization process. And you can see our method is in green. Our method can minimize the error much faster and better than the conventional method of calibrating the cameras. This is when you have good initial guess for the parameters. When we don't have a good initial guess, it shows the real value of the method that we propose. Here again, we have a log scale axis here, and our method, which is in orange here, is compared with blue, which is a conventional method. And you can see that the conventional method is basically failing in converging or identifying the parameters. But our method, even in the presence of about 200 or 100 pixel error, could converge, which is very substantial. Usually the methods can't perform well when we have more than 5 or 6 pixel shift error. This was the first step of doing the camera calibration. In the next step, we even further improved that by proposing a model-based approach. In this one, we are tackling the problem of using a checkerboard template. When we are using a checkerboard for the calibration process, we are relying on the accuracy of the checkerboard in finding the corners of the checkerboard. Here we propose a way that is helping us to avoid these problems. We propose to use a circular ring pattern, which helps us. Maybe it's break.
Keep going.
I'm close to the end, don't worry. Okay, so get back. It helps us to avoid the problem with identifying the checkerboard corners. And the other problem that we tackled here was to use Zernike polynomials as a mapping function to map for distortion parameters. This is to overcome the problems of using conventional distortion models. By using this new method, we could identify the centers of the circles, which are our control points for the calibration process. And then, after identifying the centers, we could sort them, because it's when the pattern is rotating, you should be able to identify the corners in different cameras. And you should be able to find the order of them to use them as control points. By finding the orders, then we can compare the image that we had from the cameras with the ideal image that we had from the calibration template. That's why we call it a model-based approach, because here we don't rely on the image that we see here, but we use the ideal pattern, which is the model that we know the shape should be. And by comparing these two, we can understand how the distortion has affected the parameters and how we can use these new parameters to calibrate the cameras. An example that when you zoom in, you can see that how similar the actual model and the image of the camera are. And by further comparisons and finding discrepancies, we can find both lens distortion and camera parameters in the optimization process. Using the camera parameters and image registration technique, then we are able to do 3D reconstruction. A method was proposed that how we can do 3D reconstruction when we have multiple cameras. Here are images from different camera views that have been used to find the 3D shape of the object in this case. The 3D shape was used to measure the translation of a translational stage. It was moved from 10 micrometer to 3,000 micrometer, and the algorithm was used to measure that deformation, that translation in 3D. And here are the error comparison between our method and the conventional method of doing that. Especially you can see for larger errors, we have substantially better performance. The value of error are very small, even in the presence of, even at, for example, 1,000 millimeter shift, you could find that within 1 or 2 micrometer, which is less than 0.1%. The standard deviation and mean error for our method compared to the traditional method, you can see comparison is about, for example, 30 for the conventional method, 30 micrometer, and about 2 micrometer for our method, which is, again, an important improvement. Okay, here are some of the outcomes of my thesis. Every chapter that I presented here, and some of them that I haven't presented, are now in form of either publication or are in preparation for a publication. We could get 2 patents out of the methods that I presented here. One was to cover the subpixel image registration, both 2D and the extension of that I explained, and the other was to cover the part that were related to the camera calibration. An example of using this method for identifying waveforms for carotid artery, this project was funded by MedTech and was using this method initially as the part to extract the waveform. There were some more developments done over that, especially by Emily, and the basis was using this method for identifying waveform by just looking at the videos from the neck. This is an example that Kevin did for his part 4 project using this technique for finding a 3D surface of a sample here. On the left is the actual sample, on the right is the 3D reconstructed version. And then it can be used for identifying the deformations. In this case, it's stretching. You can see that how stretching has been identified and measured, again done by Kevin. And strain and deformation measurements, again for stretching. This part was done by Debbie. And they're using the combination of image registration and camera calibration techniques. And at the end, I wanted to thank my supervisors. I had great opportunity to work with them. I'm happy about the outcomes I had, but I'm mainly proud because I did my PhD on their supervisions. Paul was a fantastic supervisor. He helped me a lot to have new ideas, to develop them, to tackle difficult problems and challenging. Thank you, Paul, for all the help you did. Martin was exceptionally good, finding small, minor errors from anything that you can imagine. Every time I started to write something new, I was trying to learn from previous feedbacks from Martin. I was really trying hard to address all of them in a way that he can't come back with more comments, but again, was full of comments. Thank you very much for and Andrew was very caring. He was the reason that I came here, was the first person who introduced me to Paul and Martin. Thank you, Andrew, and was always very helpful during my PhD to feel that I have a bigger picture to do and to feel that there is someone who cares about me. Thank you very much, Andrew. The people that I had the opportunity to work with, I was very lucky to work with some fantastic people at the ABI, from Prasad to Emily, that was the more recent person that I worked with. It's a real opportunity, and it's a real pleasure for me to work with these smart and fantastic people. I'm very happy that I had this opportunity. Bioinstrumentation Lab, fantastic guys. Thank you very much for all your support and encouragement. I'm very happy that I'm among you. Velocity was one of the outcomes of this thesis. For the idea challenge, we did it together with Emily. We won the idea challenge. Thanks, Emily, for the work you did for the velocity. And for 100K challenge, we had our very good teammates. Ed is here. Thank you, Ed. Maria Jose, thank you for all the contribution you did. And we got runner-ups. It was a bit disappointing for me, but it was a good result between 87 teams. And I think it was a very good comprehensive work that we introduced on how this project can be commercialized in industrial applications. Last but not least, Farzaneh, thank you very much. She waited all long for me to work during the day, supported me, encouraged me, and really believed on me from the first day that I can do this. Thanks a lot, and my parents who were always very loving and encouraging. And thank you all for listening to this talk, and I'm happy to answer questions.
So, thank you very much, Amir. Questions? I'm sure there are aspects of issues that you've picked up, Martin.
Yeah, there's a comma on slide.
No questions. Yeah.
Can I ask about curvature of tissue and how that impacts on your measurement technique? Is it a major struggle to deal with things? I'm thinking about tubular structures like blood vessels.
Yeah, this is a real challenge for tissues, that the shape is complex. It's not the usual shape that we see in computer vision applications. That's why for our application, we use 4 cameras to cover the surface from different angles. And we use the cameras that have better view over the surface of the object that we were looking at. In addition, we developed a method, I didn't explain it here, but we developed a method that is looking to find a perspective transformation between the cameras to make the views similar before we do the dense reconstruction between the cameras. So in short, yes, this is a challenge, and this was one of the contributions that we did to propose a method that simplify that. Still, there are much more work to do for the curvy objects. One of the suggestions that Paul has, which I think is a very good one, is to use a model-based approach, which means that, for example, for some of the tissues, we know what the shape we should look for, and then use that as our basic initial guess to refine that based on the camera images.
Thank you.
Thanks, Amir. So did you, in the course of this, did you learn much about what makes a good camera for this application, or a poor camera? I mean, is that an important issue, or is the algorithm good enough it doesn't mind too much?
Yes, certainly a better camera will help. What I found out that is some of the algorithms are more sensitive to the camera settings than the other one, especially if they are accurate and robust. They need to have a better quality camera. Exposure time doesn't change the output too much, but gain is something that we should be careful for the cameras. I tested these several cameras, and it seems that the quality of the camera is important for the measurements.
So what defines the quality? Is that just kind of noise levels, or is it more?
We have, for example, for cameras, we have quantum efficiency, which is one of the main important indications of the noise. And I think dynamic range is the other aspect that is important in the selection of a camera.
I mean, but pixel density is things like that. I mean, not just resolution, but pixel size relative to sensor
Yes,
size.
that's also an important. Usually, we use computer vision cameras which have a small pixel sizes. I've tried with some of the DSLRs. They're not as good as computer vision cameras. Usually, smaller sensors are better quality. Is there anything you want to add here, Paul?
Just that often cameras are a sort of a delicate balance between resolution and signal-to-noise ratio and quantum efficiency.
You are using monochrome.
Yes.
Yeah.
I mean,
it's part of the problem with DSLRs. This whole colour thing screws things.
I mean, the algorithm will work on colour cameras, but it's just a little bit more
It
complicated.
brings in a whole lot of artifacts.
Yeah.
So,
Yeah. It's Marty.
I'll ask a question. So in that last part, I mean, you've said about the aspects of camera calibration that you wanted to improve upon, so speed, robustness, and accuracy. But you didn't really give us a good feel for exactly how did you go about doing that. I mean, was it to do with you're dealing with the same number of camera parameters in the conventional method versus your method. So you didn't actually improve upon the actual optimization algorithm per se. You would have modified potentially the objective function, say, or did you modify, what aspects did you modify to achieve those outcomes, and why, I guess? Why do you think you actually were able to achieve it?
There were several changes we did compared to that conventional method. To deal with this problem in conventional method, what they usually do is that to exclude some of the parameters from the optimizations. They start with few parameters, optimize those, and keep some of them out of the optimization process to simplify the problem. But the CDAP method usually ended up with 2 or maximum 3 cameras for the calibration. What we did was to change both the objective function and the optimization algorithm to tackle this problem. I didn't explain it here, but because we also added two more parameters to the objective function of our method. Usually the methods only use reprojection error, but we introduced 3D measurement error and 3D length error to the optimization process. In this way, we are giving more hints to the optimization process and which way it should go.
You don't add parameters though, you added terms in the objective function.
Yes, yeah.
So more parameters is generally longer when it comes to optimization.
Yes, more constraints actually.
More constraints. Okay.
Yeah, to the optimization process. But at the same time, we had more parameters because we optimized all the parameters at the same time, simultaneously. And we do that for all the cameras at the same time. In this case, we had 4 cameras, which goes to 60 parameters optimized at the same time. And in the plus, you saw, for example, after 4 or 5 iterations, they converge, which is very good.
But again, doing everything simultaneously generally adds to the complexity of the optimization, which would increase optimization time, usually.
Yes.
Constructing the Jacobian gradients and so on. So it's intriguing that you were able to improve upon that time, given the fact that you're doing everything simultaneously.
Yes.
So is it that you were reducing numbers of global iterations, or why were you able to achieve that speed up?
I think that the major reason is that, for example, in the conventional methods, they use Levenberg-Marquardt and they use the summation of the error as an indication. We use a matrix of error, which is for each image we have separate errors that are estimating and it will help the optimization process to find the better direction. And we use also trans-region reflective to have advantage over Levenberg-Marquardt. And I think addition of more constraints to the objective function and the way to measure the error was another improvement here.
Cool. Thank you very much. I think that was a lovely seminar.
Thank you very much.